This is on elements of realizability theory, is being continued. Last lecture we ended up in a bit of discussion about realizability theory, and to recall what we did was that the network synthesis problem is that the excitation and the response, they are given, excitation and the response or some relationship between them, and the usual relationship that is given is the transfer function or the Laplace transform of the output divided by Laplace of the input under the conditions of 0 initial conditions. If this is given, the problem is to find n. That is the network synthesis problem. And as I said, the first thing that we ask is this a solvable problem? In other words, is the given h of s realizable? This is the first question that we ask. And there are various realizability constraints for linear time invariant passive networks. The constraints are that they should be causal and also stable. These are the basic two constraints that will make, as far as this course is concerned, an h of s realizable: causality and stability. As you know, causality implies that the output cannot precede the input, that is the, and it is stated in terms of the unit impulse response. H of t should be equal to 0 t less than 0, because delta t is applied at t equal to 0. This is the causality constraint, and and we also mentioned last time that in terms of the frequency domain, the causality constraint can be transformed into h of j omega, where h of j omega is the Fourier transform of h of t, and the constraint is that if we take log of h of j omega magnitude and then take the magnitude, because log could be positive or negative, divide by 1 plus omega squared and integrate this from minus infinity to plus infinity d omega, then this should be finite. This is the equivalent of this simple relationship h t equal to 0 t less than 0 in the frequency domain. That is no, it's only log of magnitude h. Well, if we take the magnitude square, it's only multiplied by 2, and therefore if this quantity is less than infinity, divided by 2 also makes it less than infinity. Okay, so it really doesn't matter whether it takes squared or not, but we are not deriving this. We are simply saying that this is the so-called Pali-Wiener criterion. But we can have a deeper look at what it implies. For example, if there is a frequency at which the magnitude of h of j omega is 0, as an example, you take the parallel T network or the bridged T network, which has a 0, which is a transmission equal to 0 at some frequency. There is a frequency of 0 transmission. Now, if magnitude h j omega equal to 0, what is log? Log is minus infinity. All right. Now, the value of the integrand equal to minus infinity is tolerable at a particular value of omega. All right, which simply means that at that frequency this quantity shall have a pole. Agreed? All network functions and analytic functions, they are differentiable everywhere except at a finite number of singularities. All right. So singularity doesn't matter. If there is a singularity and we want to make a contour integration, then what we actually do is we make a detour like this. You know this contour integration business. But suppose the magnitude is 0 over a band of frequencies. For example, you have the ideal low pass filter. Let us look at this. Ideal low pass filter is, it is unity, let us say, between some frequency omega c and 0 minus omega c, and it is 0 elsewhere. This is the ideal low pass filter. Now, in the ideal low pass filter, you see the magnitude of the transmission, this is magnitude h of j omega, This is 0 over a band of frequencies. Now, if it is over a band of frequencies, then obviously infinity multiplied by any finite non-zero quantity will be infinity, and therefore this Pali-Wiener criterion constrains that magnitude h of j omega cannot be 0 over a non-zero band of frequency. All right. In other words, it restricts that this is not a realizable magnitude function. An ideal low pass filter, any ideal filter, is not in fact realizable because it is required to be 0 over a non-zero band of frequency. Okay? This is one of the restrictions that this Pali-Wiener criterion implies, and the other restriction is that if magnitude h of j omega falls with frequency, as a low pass filter should, let us say it falls like this, on the other side also it falls like this, then this fall should not be, mark my words, more rapid than an exponential fall. It cannot decay more rapidly than how an exponential decays. Okay? Now, to make this a little more specific, let us take the Gaussian curve, the bell shaped curve, which can be represented by e to the minus omega squared. Okay? Suppose my h of j omega is equal to e to the minus omega squared, then the fall with increase of frequency is more than exponential, right? Now, if you take the log magnitude h of j omega and magnitude of this is simply equal to omega squared, and integral minus infinity to infinity omega squared d omega divided by 1 plus omega squared goes to infinity. It is not a finite quantity. This is one example, but one of the consequences of the Pali-Wiener criterion is that the magnitude squared function or the magnitude function cannot decay more rapidly than an exponential. Similarly, it cannot rise more rapidly for a high pass filter. It cannot rise more rapidly than an exponential. Okay? So, there are two consequences of the Pali-Wiener criterion which we should be aware of. There are many others, and you have to actually test by Pali-Wiener criterion, but the easier way is h of t, and for us, for circuit theory purposes, h of t would be good enough. On the other hand, suppose magnitude h of j omega, let me ask you a question. Suppose magnitude h of j omega is square root of 1 plus omega squared. Well, is it realizable? This is a trivial question. It is realizable. Why? Because we know the network. I think it's obvious when we see it. We know the network. What network does realize this? A simple RC where R and C are both equal to unity, or the product is unity. That's good enough. SC 1 by SCR plus 1, and if the product is unity, then the magnitude squared function is this. So, you know, and if you substitute this in the Pali-Wiener criterion, you will see that the integral is a finite quantity. Okay. So, in summary, we have not proved anything. We have only stated the Pali-Wiener criterion, and we have seen two consequences of the Pali-Wiener criterion, and these are good enough for an electrical engineer. That is,
the first one again, why we can't take H zero or not band of frequency.
okay. The question is, why can h of j omega, why is it constrained to have why it is constrained not to have a band of frequencies over which the value is 0. You see, if the value is 0, then log is infinity, log is minus infinity, and minus infinity magnitude is infinity. So, of necessity this integral is going to be infinite, because the integrand itself blows up. All right. That is why, however, if it is only at a particular frequency, then infinity multiplied by 0, because the bandwidth is 0. Integral means an area, the area will be equal to 0. Okay, now the second question for realizability, and that is more important in the context, is stability. And the kind of stability that we bother about in electrical engineering is the BIBO stability. That is, if the input E of t is bounded, if E of t is bounded less than equal to C1, which is less than infinity, some C1, some constant C1, then BIBO stability says that R of t magnitude should be less than equal to some other quantity C2, which is finite. This is the criterion for stability. And you know that for a linear time invariant system, causal system now, R of t and E of t, they are related by the convolution integral. Okay. So, the convolution integral is that R of t is equal to integral 0 to infinity. Why 0? Because we assume causal. Okay. H tau R of, I am sorry, E of t minus tau d tau. This is the convolution integral, and the mod R of t shall be less than integral 0 to infinity mod h of tau d tau.
Shouldn't that be integral 0 to t?
In general 0 to infinity, because we have not assumed E of t as causal signal. In general 0 to infinity, but you, if this is also causal, that is E of t does not exist for t less than 0, then the upper limit shall be equal to t. This is more general. Okay. Now, if E of t minus tau is bounded by C1, then it is less than C1 multiplied by this, and this is required to be less than infinity. Therefore, this is a re-derivation of what you did in the signals and systems course. That is, stability requires that h of tau d tau integral should be less than infinity. This you must have done in signals and systems. That is, the impulse response should be absolutely integrable. The absolute value of this integrated from 0 to infinity should be finite. Now, this is in the time domain. The frequency domain criterion is that the corresponding transfer function, that is h of j omega, must have poles, or the other way around, no poles in right half plane. What will happen if we have poles in the right half plane? Then the time domain response would increase indefinitely with time. Okay? The time domain response would have factors of the form e to the sigma t, sigma 0 t, where sigma 0 is positive, and therefore it would grow indefinitely. No poles in right half plane. If there are poles on the j omega axis, if there are poles on the j omega axis, they must be simple. Why? What is the restriction? Why is this restriction? Simple poles on the j omega axis. Why is it so?
So because in time domain we will have t tau.
Okay. If there are multiple poles, then we shall have the time domain response would contain product of t and sine or cosine of omega 0 t. Okay. If there are simple poles on the j omega axis, the corresponding impulse response shall be either sine or cosine. Okay, it can be expressed. If there are multiple poles, let us say second order pole, that is pole of multiplicity 2, then you shall have a term of this form, t multiplied by this, and this grows indefinitely as t increases. So, we can have only simple poles on the j omega axis. This also implies, if there are simple poles on the j omega axis, and we assume that h of s is a polynomial in S divided by another polynomial, that is something of the form k, let us say s to the power m plus etc. plus a0, and if the denominator is s to the n plus etc. plus b0, let me write it again. If our h of s is of this form, k multiplied by s to the m plus, let us say, a m minus 1 s to the m minus 1 plus etc. plus a 0 divided by s to the n plus b n minus 1 s to the n minus 1 plus etc. plus b 0. Okay. Then there is a restriction on the degrees of m, degrees of the numerator and denominator. You understand how we wrote this transfer function? This is in general a ratio of polynomials, n of s divided by d of s. And what we have done is the leading terms here and here we have made into unity. The constants we have absorbed in k. Alright? This will be a standard form for writing the transfer function. Now, if that is so, then what is the restriction between m and n? You see, we said that if there are poles on the j omega axis, they must be simple. That means, how can there be a pole on the at infinity? Infinity, after all, is a point on the j omega axis. M should be greater than 1, but can m be greater than n by more than 1? That is the point. No. Therefore, m should be less than or equal to n plus 1. This is the restriction. That is, the numerator degree can be less than the denominator degree. It can be constant, for example. The numerator can be a constant. For example, in 1 by SCR plus 1, well, the numerator is not a polynomial, it's a constant. So, it's a 0th degree polynomial. Now, if you take a second order network, for example, 2RC in cascade, then numerator can still be a constant unity. The denominator will be a quadratic. Okay? So, the degree of the numerator can be less than that of the denominator, but if it is greater, then it cannot be greater by more than 1. That is the restriction. This is why if you take an h of s equal to s squared, this is not realizable. Okay? Because there are two poles at infinity. You can only allow a simple pole. Now, to this realizability criterion,
Sir,
yes.
in this case, how did we prove that we require simple pole on j omega axis?
How did we?
Yes, sir.
Okay.
Sir,
If there are multiple poles on the j omega axis, then the time domain response shall contain terms of the form t times sine or cosine. You see, if we have a factor of the form s plus omega s squared plus omega naught squared, let's say whole squared, okay, then we shall have terms of the form t times sine omega 0 or cosine omega 0. And as t tends to infinity, this term blows up. It grows indefinitely. So the system becomes unstable. Any other question?
Excuse me, sir.
Yes?
So if we have m greater than n by 1 degree,
Okay.
so we will have a power of s. So we will have a term which contains s.
Correct.
So if we convert it to the time domain, we
Right.
get a delta dash t.
Okay.
So, but
H of
delta-
s equal to s.
Yes, sir. S plus something else.
Alright.
And sir, if we convert this, we get one term as
Delta prime t
yes, sir.
and the other becomes k delta t.
No, but delta prime t is not realizable. So it doesn't mean anything.
Oh, it doesn't mean anything. Well, we know that if we have this is an impedance function, s plus k. I know that an inductance realizes s. Isn't that right? An inductance, the impedance is s times L. Now, if this is a transfer function, that is a voltage ratio, then we shall have problems. We will come to that. But obviously, a network function h of s, which is an impedance function, can be of this form, s plus k. Okay, and our function h of s that we wrote was of the general form. It's not a true transfer function. It's a network function. All right. Any other question? Intimately related to this question of realizability and intimately related to testing for realizability is a kind of polynomial which go by the name of a gentleman by the name Hurwitz. Hurwitz polynomials. And and let's study what they are, because they are very intimately related to the testing for realizability. Suppose we have a network function which is n of s by d of s, okay? Then realizability demands that h of s poles must be in the left half plane, okay? Open left half plane, that is, they can be on the j omega axis also, but none on the in the right half plane, okay? D of s, therefore, and the poles of h of s are the zeros of d of s, okay? A polynomial which closely obeys this condition is the Hurwitz polynomial, okay? So one says that the d of s, the denominator polynomial, must be a Hurwitz polynomial. Now let's see what Hurwitz polynomials are.
Can you just repeat what the conditions are?
Okay, conditions are for realizability of h of s, we want its poles to be in the left half plane, including the j omega axis, okay? That is closed left half plane. Such polynomials whose roots are in the closed left half plane are called Hurwitz polynomials, and therefore the realizability constraint can be stated in terms of Hurwitz polynomials rather than saying where its poles should be. If poles occur on the j omega axis, they should be simple, and so on and so forth.
So that means it is defined in terms of the zeros of any function.
Poles of h of s are the zeros of d of s.
So the condition, the criterion of Hurwitz polynomial.
Pardon me?
Suppose of numerator as well.
Okay. The numerator, as you will see in the case of an impedance function, the numerator also has to be Hurwitz, because you know for a driving point function, poles as well as zeros should be in the left half plane. So we will apply that to n of s also, okay, when it comes to that. But let me define first what a Hurwitz polynomial is. A polynomial, this is the definition. A polynomial p of s in general is defined to be Hurwitz if and only if two conditions are satisfied. That is, it should be a real polynomial, that is p of s should be real for s real. What does that mean? That means that since it is a polynomial, it should be of the form ai s to the I, let's say I equal to 0 to n. Then it p of s real for s real means that the coefficients ai must all be real. That's all, as simple as that, okay? And the second condition is that roots of p of s should be, or put it this way, no root in RHP. P of s cannot have any roots in the right hand plane. This statement that no root of RHP can be amplified like this. That is, suppose P of, let's say, Sk is equal to 0. Okay, P of Sk is equal to 0. K equals to, let's say, 1, 2. If n is the degree of the polynomial, then the fundamental theorem of algebra states that every polynomial of nth degree will have n roots, therefore k will go from 1 to n. So the second requirement, that no root in right half plane, means that if p of sk equal to 0, that is sk is one of the roots where the subscript k goes from 1 to n, and sk equal to, let's say, minus sigma k plus j omega k, where this is the real part and this is the imaginary part, okay, then what does it mean? It means that sigma k must be greater than or equal to 0, because it is the closed left half plane. The real part of the roots must be non-negative. One of the ways of expressing this greater than or equal to 0 is that the real part should be non-negative. All right. Any question? Our polynomial we took as summation ak s to the k k equals, oh no, I took I, isn't it? ai s to the I, where I is equal to 0 to n. Alright. Let's look at this a little more closely. P of s is equal to ai s to the I equal to 0 to n. Now, I have already said that this ai, this coefficients must be real, because how it's polynomial demands that the polynomial be real for s real. If s is real, then ai obviously have to be real. Okay. What about sign? Can some of the coefficients be negative? The answer turns out to be no. We cannot have a negative root. Let's see why. Let's see why. The roots that are permitted for P of s belong to these locations. There can be a root on the negative real axis. Okay. Let's say this point is minus gamma I. Okay. So this root will contribute a factor of s plus gamma I. Isn't that right? This root will contribute a factor of s plus gamma I. This is one possible root. Another possible root could be a pair on the j omega axis. Let's say this is omega j. Why 2? They must be complex conjugate because the coefficients are real. Correct. So what do these two roots contribute? What factor? Obviously s squared plus omega j squared. Alright. These two roots contribute to a factor like this. And the only other possibility is that we have roots like this, complex conjugate. Alright. Let's say this distance is omega k and this distance is, let's say, minus alpha k. Alright. These two roots contribute to a factor of s plus alpha k whole squared plus omega k squared. Is this clear? These two roots contribute to a factor of this form, because what you have is s plus alpha k plus j omega k multiplied by s plus alpha k minus j omega k, and if you multiply this out, this is precisely what you will get. Alright. Okay. So in general, these are the only three possible forms of roots. You can't think of any other. And the polynomial must be a product of factors like this. That is, you can have continued product of factors like this, continued product factors like this, and continued product factors like this. In these component polynomials, all coefficients are positive, and by multiplying a number of component polynomials in which the coefficients are positive, you can never get a negative term. Isn't that right? Is this right or wrong? Which means that the coefficients ai's must be positive. ai's are real and positive. Agree? If you see a network function in which the denominator contains a complex coefficient, immediately you can throw it out. It's not realizable. If you see all coefficients are real but one of them is negative, immediately you can throw it out. Okay. Now next question.
You're talking about the denominator?
Denominator, yeah. In general, for impedance functions, the numerator has also to be tested. Yes.
Should A be real and non-negative?
That is the question I am going to ask you now. Okay. Whether we should call it positive or non-negative. Let's say P of s, once again ai s to the I equal to 0 to n. The question that I am going to ask you is, between a0 and an, can there be a missing term?
Yes.
It can be. Now, how can a missing term be created from product of factors like this, how can you think of a missing term? There cannot be. The answer is there cannot be, unless you have a term like S minus gamma I, when, because missing terms requires cancellation, and cancellation can occur only if in one of the components there is a negative term. Obviously there cannot be a negative term here unless this is minus alpha k. There cannot be a negative term here at all. These are both positive.
So suppose you have only second term, for instance, S square plus omega j square and S square plus into S square plus
Okay,
omega I
okay, that's a good question.
Can you please explain it again?
Good question. What he says is, if I have terms only of this form, continued product over J, yes, there are missing terms possible. But it's a very special case. What is the special case? That it is a purely even polynomial. It's a purely even polynomial. And it is Hurwitz, because its roots are not in the, none of the roots are in the right half plane. Okay, so you must qualify that in general there cannot be a missing term between A0 and AN unless all odd terms are missing. That is, unless the polynomial is purely even. And we are being a bit biased when we are saying purely even, because such a polynomial, if multiplied by S, also shares the same property. If you multiply by S, then the polynomial becomes purely odd and all even powers are missing. Therefore, you should say that in general no term between A0 and AN should be missing unless all odd terms are missing or all even terms are missing. Alright, that is unless the polynomial is purely even or purely odd. Now I look at the question. I ask you a question. Unless you have a question.
So how it makes difference that some of the terms are missing?
How it makes a difference? Okay. If let's say you have a term S cube plus S square plus 1, then the coefficient of S is missing. How can that coefficient be missing unless there are cancellations? Unless there are cancellations. You see, our only terms are S plus gamma I, S square plus omega j squared and S plus omega k squared, no, alpha k squared plus omega k squared. By multiplying such terms, you can never get a missing term unless either this gamma I is negative or alpha k is negative. That means roots in the right half plane. Any other question? Now let me ask my question. Suppose you have a polynomial S to the 4 plus 1. It's purely even? It is purely even? Is it Hurwitz? No, because one of the even terms is absent. You see, you can allow the polynomial to be purely even or purely odd, provided there are no missing terms again. You can allow all odd terms to be missing, but no even term should be missing. If it is even polynomial, all even terms should be there. Missing means that there are roots in the right half plane. Can you show this here? It's very easy. You can write this as twice S squared plus 1 minus twice S squared. So this is S squared plus 1 plus root 2S, S squared plus 1 minus root 2S, and you can see that this is a non-Hurwitz polynomial because there is a negative coefficient. Is that clear? We shall have lot of fun with Hurwitz polynomials and Hurwitz polynomials play a very important role in circuit theory, in network synthesis. Now suppose I have a P of S which is purely even, no missing term. Where do you think its roots shall be?
It's purely even.
Purely even with no missing, they must be on there. Similarly, if it is purely odd, then also its roots must be on the j omega axis only
And
with
0.
with one root at the origin. Can there be two roots at the origin? No. If it is odd, then there cannot be.
one.
Can you have three roots on the origin?
Yes.
Yes, you can. But if there are three roots at the origin, then the function is useless for network synthesis. Why? Multiple poles of them. Absolutely wonderful. That means Hurwitz polynomial has soaked in. Okay. Suppose P of S in general, it's a Hurwitz polynomial with its even part denoted by small n and its odd part denoted by n of s, small n of s. Then one of the properties, and this is the test for a Hurwitz polynomial. The test for a Hurwitz polynomial is that the ratio m to n, the ratio of the even part to the odd part or the odd part to the even part, depending on which one has a higher degree. Suppose P of s, the highest degree, highest power is even, then you should take the ratio m by n. Pardon me? Oh, m is the even part. I think okay. Small m is the even part of P of s and small n is the odd part of P of s. For example, if I have, let's say, s squared plus s plus 1 P of s, then m is equal to s squared plus 1 and n is equal to s. Even part and odd part. Alright? And the ratio that you should take now is s squared plus 1 divided by s. That is, you should take the higher degree polynomial in the numerator and the lower degree one in the denominator. What can be the degree difference between these two, m and n? Can it be 2? Why not?
Can be 3.
Why not 2?
Because
Because one is even and the other is odd. So the difference must be odd. Okay. It cannot be 3. If it can be 3, but then we shall not be interested in it. Okay. All right. Now, one of the properties of a Hurwitz polynomial is, and this property leads to the testing of Hurwitz polynomials, is that this ratio m by n or n by n, putting the higher degree polynomial in the numerator, if you make a continued fraction expansion of this or this, depending on whichever is applicable, the continued fraction expansion of this shall yield positive quotients. It can be rigorously proved, but we are not interested in the proof. The testing of a Hurwitz polynomial says that the continued fraction expansion of m by n or n by n will yield positive quotients. Okay, positive quotients. Now, quotients obviously I'm not. This is not quite correct. What will be the form of the quotient? Suppose I divide s square plus 1 by s. If I expand this into continued fraction, the first quotient will be s. Now, what do you mean by positive s? No, positive coefficient quotient. All right. The continued fraction expansion should yield positive coefficient quotient. Before I take an example, tell me, will this continued fraction expansion, will it always be finite? Or is there a possibility that it can go on and on like a recurring decimal? Continued fraction expansion, will it be finite or shall it continue
So if it
indefinitely?
is realizable,
It has to be finite. How many quotients do you expect? How many quotients? Continued fraction expansion, well, you have forgotten what is continued fraction expansion. It would be
depending on the difference between the degree of numerator.
difference
No, sir, depending on the degree of numerator.
depending on the degree of the numerator, which is also the degree of the polynomial. Isn't that right? Therefore, continued fraction expansion, one of the properties is not of Hurwitz polynomial, any continued fraction expansion shall be finite. And the number of quotients that you expect is equal to the degree of the polynomial. For example, if you have a cubic polynomial like this,
But
s
it will be
cube,
finite only if the it is a realizable.
no, any, it is realizable or unrealizable, it doesn't matter. Harwitz or not, it doesn't matter. If you have a cubic polynomial, for example, the continued fraction expansion would be of this form: s cube plus 2s, you shall divide by 3s square plus 1, alright, s by 3, s cubed plus s by 3, what am I left with? 5s by 2, 3s square plus 1, 5s by 3, okay. So this will be 9 by 5 s, so 3s square, 1, 5s by 3, 5s by 3, and that's it. Continued fraction expansion ends. I have exactly 3 quotients, the coefficients of which are positive, and therefore I conclude that this must be a Hurwitz polynomial. This I did only to illustrate the number of quotients is exactly equal to the degree of the polynomial. Now it may so happen in Hurwitz testing, it may so happen that you don't get this required number of quotients. In other words, the continued fraction expansion may end prematurely. Is that possible? It is possible only if the even part and the odd part have a common factor. For example, if this polynomial is multiplied by s square plus 1, alright, then what is the degree of this polynomial? Degree will be 5, but you shall get exactly 3 quotients, because in forming, what shall you form here? N by n. In forming n by n, n has a factor s square plus 1, m has a factor s square plus 1, and therefore the number of quotients shall be exactly equal to 3, not 5. In other words, there is a possibility that the continued fraction expansion will end prematurely, and if it ends prematurely, that shows that the even part and the odd part have a common factor, and this common factor, if an even polynomial, let me go slow, if an even polynomial and an odd polynomial has a common factor, what can be the form of this common factor? Do you understand what I mean?
S plus alpha. But
It cannot be s plus
It
alpha.
has to be a s square or s.
It has to be an even polynomial, and this is why we said s square plus 1. Okay, and how do you detect it? Let's before taking an example, suppose I have, let's say, s squared plus omega j squared, a number of them. Suppose this multiplies in m of s plus n of s. Suppose I have a number of factors. How do I detect these factors? Because in the continued fraction expansion of the even part divided by odd part, or the reciprocal of it, I shall get a number of quotients exactly equal to degree of m plus n. These factors, how do I discover? It requires a bit of thinking to convince oneself that these factors will make their appearance during the continued fraction expansion. In fact, the last divisor shall be proportional to these cancelling factors. The last divisor. After that, there is no other divisor because the remainder is 0.
this thing is not clear.
So
Okay.
Please explain on the last page, sir.
Maybe I take an example, then I will come to the theory. Let me take an example. Suppose I have s to the 7 plus 2s to the 6 plus 2s to the 5 plus s4, fairly non-trivial example. 4s cubed plus 8s squared plus 8s plus 4. This is my P of s. And the question being asked is this Hurwitz or not? So what we do is we make a continued fraction expansion like this: 2s to the 5 plus 4s to the 3 plus 8s I divide by 2s to the 6 plus s to the 4 plus 8s squared plus 4. Okay, so I get half s as the first quotient. I get s to the 7 plus s to the 5 by 2, then plus 4s cubed plus 2s. Agreed? Please don't allow me to make a mistake. Is that okay? So I get this will be 3s to the 5 by 2. All right, these two cancel, plus 6s. Is that right? All right. So I divide 2s to the 6 plus s4 plus 8s squared plus 4. Now what do I get? 4s divided by 3. This is the quotient. Don't allow me to make a mistake. So it's 2s to the 6 plus 8s squared. 8s squared. So I am left to it s to the 4 plus 4. All right. So let's bring 3s to the 5 by 2 plus 6s. All right. Then what do I get? 2 by 3s. 3 by 2s. Can I slow down? Okay. Of course I can. Where did you lose yourself?
It's not lost, I know, but I might.
Oh, you might. All right. Prevention is better than cure. We shall do that. 3 by 2s. So I get 3s to the 5 by 2 plus 6s. And you see that I expected 7 quotients and I end up with 3. The last divisor must be of degree 4. I have got 3, I have missed 4 of them. The last divisor must be of degree 4, and the last divisor is the common factor, not the common factor. There could have been a constant, for example 2s4 plus 8. The last divisor is a constant multiplied, the constant here happens to be 1. Last divisor is the common factor, and therefore P of s shall have a factor of s to the 4 plus 4 multiplied by P1 of s, some P1 of s. Okay. Do we have to go further to test whether P of s was Hurwitz or not? Do we have to go further? No, because this polynomial is non-Hurwitz.
Yeah.
Isn't that right? Because there is a missing term here. S squared term is missing. But suppose there were no missing term. Suppose this was Hurwitz. Then you had to test P1s for Hurwitz character. Is the point clear? This is only one step. If it ends prematurely, you discover the common factor. You take the common factor, call the rest of the polynomial as P1. If the common factor is itself Hurwitz,
So that means we have to divide s4 plus 4 by the ps and find the.
that's right. You have to divide this given polynomial P of s by s4 plus 4, find out what is P1 of s, then subject P1 of s to Hurwitz character, Hurwitz test. Is that clear? And then only at the end of this exercise you will be able to say whether it is Hurwitz or non-Hurwitz. Now this is a purely even polynomial, but its roots are not all on the j omega axis. Okay, if there are common roots shall be discovered by Hurwitz testing. All right, and can this polynomial, for example, be odd? Can the last divisor be odd? No, it shall be even. With caution, I make this statement with caution. You might have to disappoint yourself later. suppose now another tricky question. Suppose P of S is given as, let's say, s to the 8 plus 6s squared, no, 6s to the 6 plus 3s to the 4 plus 2s squared plus 1. Now this is the polynomial that is given. That is, it's a purely even polynomial. How do you test this? Because its odd part is 0. On the other hand, this could be a Hurwitz polynomial. If all its roots are on the j omega axis, this could be a Hurwitz polynomial. Alright? Then the method of testing is, again without proof, if you are given a purely even or a purely odd polynomial, it applies to odd also, what you do is take the first differential coefficient, P prime s. Obviously, P prime s shall be purely odd. And then you make a continued fraction expansion of P of s divided by P prime of s, first differential coefficient. And if this satisfies the criterion, that is, it does not end prematurely, number one. Number two, all its quotients are positive, then P of s is
So
Hurwitz.
if it ends prematurely, it does imply that it is not.
Non-Hurwitz, correct. If it ends prematurely, then you shall have to subject the
So it
remainder
doesn't-
polynomial. Correct.
So it doesn't imply that it is non-Hurwitz.
Correct. That's what I'm saying. If it ends prematurely, then you have to discover the common factors. You have to discover P1 of s and then subject both of them to Hurwitz test.
If they come out to be Hurwitz, then it is.
Yes. In this particular case, this was by inspection you could see that it is non-Hurwitz, so you could discard it. But suppose you cannot do that by inspection, then you have to subject both of them to Hurwitz test. Alright? For example, if I take this polynomial s to the 4 plus s squared plus 1, suppose this is my P of s, then P prime of s is equal to 4s cubed plus twice s. Okay? Now, shall I divide? That's another question that I want to ask. Shall I divide by 4s cubed plus 2s, or can I divide by 2s cubed plus s? 2s cubed plus s. Can I do that? Why can I do that?
Keep in mind that I have a 2 of it.
All I want is whether the quotients are positive or not, and dividing any part by a positive constant doesn't matter. This is a simplifying feature, otherwise we will have to handle large numbers. Alright? So I can do that. I get s by 2, s to the 4 plus s squared by 2. What I am left with is s squared by 2 plus 1. Then I divide 2s cubed plus s. This is how continued fraction is made. I take this as the what is it called? Dividend. So I get how much? 4s, 2s cubed plus 4s minus 3s. Do I have to go further? No, because the next quotient will be negative. Therefore, this is non-HP, non-Hurwitz polynomial. Okay. Now, in tomorrow's class, yes, I'm aware. In tomorrow's class, we shall continue the discussion of Hurwitz polynomials and their importance in testing network functions. That's all.